This video will be going over section 3.7 on rational functions. The first thing we'll do, we'll talk about what a rational function is. Then we'll hit on pretty much all the characteristics of a rational function that are different than a polynomial. So one thing we'll have to worry about is the domain of a rational function, and what goes along with that are topics called vertical asymptotes and holes. The second thing that's new kind of goes along with our polynomial stuff that we've been doing, the end behavior of a rational function. Now, rational functions, a lot more can happen. With polynomials, the end behavior is always infinity or negative infinity, and with rational functions, it can be any number. But it's also always a significant thing, so we actually will refer to that as horizontal asymptotes, as you'll see. Then I'll just have a problem of putting it all together. If you have a rational function, what are all the things you can figure out about it? X-intercepts, Y-intercepts, asymptotes, domain, all that stuff. And then the last little bit will be on the graphs of rational functions. Can you give me the formula for a rational function if you're given a description? Can you give me the formula of a rational function if you're given a graph, like we did with polynomials? And if you were comfortable with the polynomial stuff, this adding in the rational function things isn't too much. So the definition of a rational function, it builds on polynomials. If f and g are polynomials, then a rational function is just f of x divided by g of x. Okay, so it's a polynomial divided by a polynomial. If you have a fractional function is the top of polynomial and the bottom of polynomial. If the answer is yes, then it's a rational function. So I have a few examples here. First one, f of x equals 3x plus 3 over 4x minus 1. The top and bottom are both polynomials. Since they are both polynomials, this is a rational function. It doesn't matter what degree they are or anything like that when we're asking this question. It's just, is the top, is the bottom, are they each polynomials? Second one, same deal. The top 3x squared plus 3x to the fourth minus 1 and 4x minus x to the sixth are both polynomials. So that is in fact a rational function. And the last one, a pretty simple example, but we talked about why numbers are just polynomials. So 1 over x is also a rational function. The function 1 is a polynomial of degree 0. The function x is a polynomial of degree 1. So all three of these are rational functions. Pretty much if you compare rational functions to polynomials, we can now have x's in the denominators because of the fraction thing. We still cannot have any radicals. You will not see any radicals in this entire chapter. But this is the last section of the chapter. So the first thing to talk about, because rational functions have denominators with x in them, sometimes you can divide by 0. Right, for this third one here, if we plugged in 0, we would get 1 over 0, which is bad. Right, that's going to be a problem. And that's corresponding to the domain of a rational function. Right, this is something you've probably done before in college algebra. To determine the domain of a rational function, you set the denominator equal to 0 and solve for x. And the domain is all real numbers except the x values you find. Okay. Now, one thing you'll see with one of the examples I have, we'll have a rational function with an x in the denominator, but you don't have any values that make it 0, and that's fine. You don't have to get any x values when you solve this part. So don't force yourself to have them. The x values not in the domain of a rational function have two possible outcomes. They're either vertical asymptotes or holes. There is no other option for them. And I have here described how you tell the difference. We'll do it in the problem so you can see it as well. To determine which occurs algebraically, what we do is we factor and cancel, if possible, on the top and bottom. So imagine if we factored this thing up here and could cancel stuff out or not. Any x value making the denominator 0 after canceling has a vertical asymptote, and any x value that no longer makes the denominator 0 has a hole. So if it gets canceled out, it's a hole. If it doesn't get canceled out, it's a vertical asymptote. Right, so this stuff goes together. Often you'll kind of see that really in the homework as well. We have a couple problems here. It says for the following rational functions, determine their domain and write it in interval notation. Then give the x values of all holes and the equations of all vertical asymptotes. All right, so what we'll do is we'll work through this problem. I'll graph it so we can sort of explain what's going on, make sense of it, and then do the same thing. It's also interesting what happens with holes with the graphs is you can't really see them, which we'll find out. So there's no way just graphing this you can figure it out. You have to actually do it the algebra out. But for the domain, we start by setting the denominator equal to 0 and solving it. It doesn't matter what the numerator is. That can be 0. It cannot be 0. There's nothing wrong with it. And our denominator is 4x minus 1 times x plus 4. They've already factored it for us, which is nice. We set each one to 0. We've been solving things like this all this chapter now. You're probably a little more comfortable with just listing out the answers. But I'll just do it out to do it out. We set each one equal to 0. 4x minus 1 equals 0 and x plus 4 equals 0. And the one on the left here, we add the 1 and divide by the 4. We get x equals 1/4. And the one on the right, we subtract the 4 and we get x equals -4. So one thing to really remember here, the two x values you found are the two not in the domain. Everything else is in the domain. And I believe in this class we haven't actually written a single thing in interval notation. I'll do this once just to remind you how you can figure out the domain in interval notation or anything in interval notation using a number line. What you do is you make a number line and you mark off your two or all the x values you get, which we have 2, -4 and 1/4. Because these are not included, they get open circles around them. So remember, when you make a number line, well, at least one of the ways you do it, I know many people do it a lot of different ways, but one way to say I'm not going to include a number is by making an open circle on the number. But we do include everything else, right? We're only throwing away these two numbers. We want to include everything to the left of it. We want to include everything in between it. And we want to include everything to the right of this one. And if we write this down in interval notation, we start at -infinity all the way to the left. We go up to -4. Open circle means it's not included, so we put a parentheses. When we have more than one interval, we do a union. And then we hop right over. So we're still at -4, just on the other side. We start at -4 and we go all the way this section to 1/4. Once again, parentheses because we're not including the 1/4. And we have one more interval. We do another union. And we have where you just jump over the 1/4. And there's nothing stopping us going to the right. We go all the way to infinity. Right, so this is the domain in interval notation. This is what you type in the homework. And all this stuff in our homework software. Click that little up arrow, click on the interval tab and you can find everything here. You just gotta click, set it up, and then type in the numbers. All right, so this is the domain. Now what we want to do with these numbers specifically, 1/4 and -4, are there vertical asymptotes there or are there holes there? So we got x equals -4 and x equals 1/4, not in the domain. So the question to answer, do we have holes or vertical asymptotes? Right? That's just the preliminary thing we talked about here. When you have a rational function, those are the only two possibilities. So the question is, do we have a vertical asymptote or a hole at each? You can only have one or the other at each. They could both be holes. They could both be vertical asymptotes. They could be one can be a hole, one can be a vertical asymptote, but it has to be one or the other. Well, the thing that I mentioned up here, which I'll go back to one more time, to determine which occurs, we factor and cancel if possible. All right, so what you want to notice here, this is factored for us, and there's no common factors. There's no common factors, so nothing cancels. Right? You could, if you wanted to, factor a 3 out of the top to make x plus 1. If you want to view it as like fully factored, x plus 1 doesn't cancel. Factors only cancel if they are exactly the same. That's why it's very important to factor your stuff all the way so you can tell if it's exactly the same. So nothing cancels. What that means, once again, we'll go back here to remind you, any x value that still makes the denominator 0 after canceling has a vertical asymptote. Okay. What still makes the denominator 0? Well, both of them, because they didn't cancel. Let's go ahead and write that. Both still make the denominator equal 0. If we plug in -4, we get 0 here. If we plug in 1/4, we get 0 here. That means there are vertical asymptotes at each one. And what we would say is they're vertical asymptotes of x equals -4 and x equals 1/4. So we'll see this with the graph, but vertical asymptotes, you should have seen them before. They are basically these invisible vertical lines that the graph doesn't touch. Since they are vertical lines, they have an x equal equation, and the number is the number we've got over here. And so they are both vertical asymptotes. Now, once you see that, since every one of these points is a vertical asymptote or a hole, and they are both vertical asymptotes, that means there are no holes for this one. And I'll just remind you the way I know that. Any x value making the denominator 0 after canceling has a vertical asymptote, and any x value that no longer makes the denominator 0 has a hole. Basically, I think about it, cancel, whatever cancels out gives a hole, which is nothing. What doesn't cancel out gives us a vertical asymptote. All right, but what I'm going to go ahead and do is graph this so you can see the vertical asymptotes in the calculator. I'll go to my calculator. We got y equals, the numerator was 3x plus 3. You want to be careful, just put the entire thing, numerator and denominator, in parentheses so it goes in the correct spot. The denominator 4x minus 1, and x plus 4, I believe, yes, x plus 4. Now you want to make sure you include these extra set of parentheses, because if you don't, then it's going to read it as the 4x minus 1's in the denominator, but the x plus 4 is in the numerator. So make sure you include the extra set of parentheses around the whole thing. And we'll go ahead. I don't know if I've messed around with the window. I'm going to hit zoom and 6, standard window here. We'll make it look pretty, for lack of a better term. And what I want to point out here, I can't draw on this thing. Unfortunately, I can only point at it. But we had two vertical asymptotes, negative at -4 and 1/4. If you look at x equals -4, we have this vertical separation of the graph. Now this goes straight down. What is going to happen is it's going to go down to -infinity, but it's never going to be at -4. It's almost like having an invisible dashed line here. And then it just pops over the other side. This one happens to come from the top. And then we're on part of the graph again. And then 1/4 would be about right here, because this is 0 and this is 1. And you can see the other vertical asymptote. This one's going down to infinity. And then this one goes up to infinity over here, either touching those numbers. And one thing I can point out here, if you hit the second graph button, it brings up this table. Most of them are automatically set up like this, where it has 0, 1, 2, blah, blah, blah. And if you scroll up, you should have the negative integers. If you hit second table set, this is what I always tell everyone at the beginning of my classes. For the independent variable on auto, if you switch over to ask and highlight that and go back to the table, what you can do is type in the x values you want to. So if I type in -4 and if I type in 1/4, you'll get an error for both. Now that error means these numbers aren't in the domain. It doesn't tell you whether you have a vertical asymptote or a hole. That comes from what we did and is confirmed by the graph. But these two numbers are not in our domain. If we type in any other number for, I can type in 1/5, kind of close to 1/4, but not really. It's gonna spit out a number, -100 million, whatever. Just click a whole bunch of zeros. It's gonna spit out a number, whatever that is. So there's not really going to be any issues with any other numbers, as there shouldn't be. But I did want to point that out. If you type in the x values that are not in your domain, you should get errors. If you get errors, you still can't tell which is which. These both happen to be a vertical asymptote. But the next one, we will have an example of a hole. I can show you what happens with the graph of that. And so this one's not factored for us. It looks kind of weird because of this -2 out here. You just want to leave that alone when you figure out everything about this. Really, we can always distribute the number out front to the top, but that makes it more complicated. So leave this -2 out here. You don't want to get rid of it. Just leave it out there. But it's the same directions as the last problem. I'll scroll up and remind you, we are figuring out the domain and interval notation. We are going to give the x value of all the holes and the equation of all the vertical asymptotes. The first thing, let's figure out the domain. So we set the denominator equal to 0, x squared minus x minus 30 equals 0. And typically in this section you have a lot of work to do. Otherwise you can factor most things, but if you can't factor something, you can use the quadratic formula. There won't be anything crazy to do like last section. But you can factor this. This factors to x minus 6 times x plus 5, which equals 0. And this one I'm going to use what we did in the previous sections. Since this is x minus 6, this is x plus 5, we get the opposite. We get x equals 6 and x equals -5. But you can also see that if you set each one equal to 0 and solve it. Now what I want to remind you here, these two numbers are not in the domain. At each one of these, we're going to have a whole or a vertical asymptote. But they are not in the domain. When I put this in the calculator and do that table thing, when I hit 6 and -5, I will get an error no matter what. I'm not going to do that yet. All right, these are not in the domain. The domain and interval notation. If you made a number line, it'd look exactly like this. We would mark off -5 and 6. So the domain and interval notation. We start all the way from the left, go up until we hit our first number. Be careful here. The first number is -5, the smaller one. Parentheses, because we're not including it, union. We jump over the -5 and up to 6. Parentheses, because we're not including it, union. And then we jump over the 6, and there's nothing else stopping us. We're going to infinity. It's supposed to be a parentheses, and I'll make it more round. But that is the domain in interval notation. Now the question is, what's happening at each of these values? This one is not factored for us. We factored the bottom already, which I'll use. We need to also factor the top. So to figure out whether we have wholes or vertical asymptotes or one of each, we must factor numerator and denominator and cancel. Right. Now the -2, yeah, I think it's a good idea to leave it there so you don't completely disregard it. If you had more to do with the problem, you wouldn't want to get rid of it, but just leave it out front. The denominator we already factored to x minus 6 times x plus 5. And the numerator, what does that factor to? X squared plus x minus 42 factors to x minus 6 times x plus 7. And so we got this factored. Now we ask ourselves, does anything cancel? And yes, x minus 6's cancel out, but these don't cancel. All right, so let's go ahead and think about the question now. What is a vertical asymptote? What is a hole? Well, vertical asymptote is what didn't cancel out. And what's going to make that 0 is the -5 one. Right, so x plus 5 equals 0. That's gave us the -5. So the equation of a vertical asymptote is -5. Everything else, all the other x values, are holes. Everything that canceled out. And we have a hole at x equals 6. 6 is what's canceled, but once again, you're taking them all from these numbers. All right, so that's the way I like to do it. Just see what cancels out, especially if you write it out and have it factored out here. You can see it pretty easily. You don't have to try to memorize or remember what was up here necessarily. But for this rational function, we have a vertical asymptote at x equals -5 and a hole at x equals 6. Now what I'm going to do is graph this thing. I'm going to graph it exactly the way it was at the beginning. Go back to y equals. We had our -2 out front times, and the numerator we have, once again, put it in parentheses, x squared plus x minus 42 divided by the denominator, which is x squared minus x minus 30. That'll give you your picture. We didn't mess with the window, but you can always hit zoom 6 to see a nice picture. And now I'll go back to what we figured out. There's a vertical asymptote at -5. If we go -1, 2, 3, 4, 5, that looks correct. It's going to go straight up. This one happens to go up from the left side of the vertical asymptote, and this one goes down from the right. It can do any combination of things. So that is fine, but it looks like it's being separated here. We got the right value. Oops, wrong one. And then we had a hole at x equals 6. So this is what's pretty tricky about holes, is if you just graph these things, you're not going to find them. Because if you look at where x equals 6, we got 1, 2, 3, 4, 5, 6 right here. If you look at the graph, you don't see a hole. Right? Typically, if you're told a hole that's on the graph, someone will fudge the graph to make a hole. Very literally, they'll draw an open circle on the graph. But when you graph one yourself, you won't see the holes. However, if you look at the x value or the y value right here, it looks like it's like -2.5 or something. If you go to the table, if you type in the -5, that was our vertical asymptote, when we get an error. If we type in 6, we also get an error. What that's telling you is there is a hole at that graph. It's not really there. The problem with graphs is holes are so tiny that you can't actually see them. So that's one thing you got to be careful about with graphing these things, is you can't rely 100% on your calculator to figure out if there's a hole. I mean, you know, you can kind of check your answers. You know, if you figure out the domain and what's not in it, then you can graph it, see what the graph looks like, type in your numbers. But you're going to have to do this work anyway to show you know the difference. The graphing calculator is just to confirm or not confirm your answer. But what we'll see in the end of the section when we talk about graphs, we won't deal with holes for those because you cannot see them. Since you can't see them, we can't expect you to be able to magically know when they are being used or not. All right, so the next little section, these are really best explained by me just talking about the 3 examples. And then I have a couple problems after that will actually work it as well. But the end behavior of a rational function, like I said at the beginning, is much more varied than that of a polynomial. It's so varied that we don't really actually call it end behavior. We call it a horizontal asymptote. Right, so what you'll find in a lot of the homework problems, you won't be asked the end behavior of a rational function. You'll be asked, what is the horizontal asymptote? And there are 3 possibilities. You might have a horizontal asymptote. You can have 1, but you can also have 0. And so f of x I'm representing with the top and g of x with the bottom. Now these examples I would write down the whole thing. I didn't want to highlight the whole thing here. I thought it might look kind of weird. But I'll talk through each of them. So if the degree of f of x, which is the numerator, is larger than the degree of g of x, which is the denominator. So the degree of the top, x cubed, for my example here, x cubed plus 3x minus 1 is 3. The degree of the denominator here, x squared plus 1 is 2. Right. The degree of the numerator is larger than the degree of the denominator. Then what happens is there is no horizontal asymptote. Right. So there is no horizontal asymptote. What horizontal asymptotes will look like, I'm going to graph each one of these to sort of explain it as well. But they kind of think about a vertical asymptote like this invisible vertical line where the graph never touches. A horizontal asymptote is the same idea. it's going to be this invisible horizontal line where the graph never touches as you move all the way to the right, all the way to the left. All right, so for this example, x cubed plus 3x minus 1 over x squared plus 1 has no horizontal asymptote. You write D and E in the homework, it tells you to do that. But it doesn't matter how much larger the degree is on the top. This could be 7, this could be 1. As we have with this example, it could be 1 larger, it can be 10 larger, 100 larger. As long as it's larger, there is no horizontal asymptote. All right, so I'm going to go ahead and graph this in the calculator to really explain what we're talking about here. All right, so we got, I already forgot what it was, x cubed plus 3x minus 1 on the top. Divided by the bottom, x squared plus 1. Now if I hit graph, horizontal asymptotes, like I mentioned, they are, what you're going to see is that the graphs really flatten out. But this one's going to keep going up this way, this one's going to keep going down this way. If you don't necessarily believe that, you can zoom out and see that's going to happen. This one's just going to keep going up, this one's just going to keep going down. It almost looks like a line. There are reasons for that. The main reason is the degree is 1 larger on the top than the bottom, but we don't really need to remember those specifics. What you want to notice here is there's no horizontal asymptote because it's not flattening out. Right, now the second example here, what happens if the degree of the denominator is the bigger one? Right, so if the degree of the denominator g of x is larger than the degree of the numerator f of x, then there is a horizontal asymptote, and it's always y equals 0. Right, horizontal asymptotes are horizontal lines, so it's going to be a y equals equation. If the degree of the denominator is larger than the degree of the numerator, then it's y equals 0. It doesn't matter how much bigger it is, it's always 0. It doesn't matter what numbers there are involved, it's always y equals 0. So for example, x squared minus 3x minus 1 divided by x to the 4th plus 1 has a horizontal asymptote of y equals 0. I'm just going to go ahead and also graph this one, and we can see what a horizontal asymptote actually looks like. I think what I'll do is I'll put these two graphs on the same picture. That way we can really see the difference. All right, so the top, x squared minus 3x minus 1. And the bottom was x to the 4th plus 1. All right, I'm going to hit zoom 6 to get in the standard window. That was our original one, the blue one. The red one is our new graph. Right? So horizontal asymptotes like in behavior. What y value are we going to as we go to the right? What y value are we going to as we go to the left? Well, they're both pretty much riding along the x-axis, which is y equals 0. It doesn't matter what's happening close to the y-axis. It matters what's happening to the right and to the left. They're both going towards 0. If we zoom out, that red line is just going to stay there. It looks like it's at y equals 0. Okay, so that's what a horizontal asymptote looks like. They can obviously vary in range. This one's really flat. You'll see with the next one, I believe, it's not going to be as flat. They can look very different. As long as it's flattening out, you'll have a horizontal asymptote. All right, so the last example here is when the degrees are the same. If the degree of the numerator and degree of denominator are equal, that's the one example that doesn't get encompassed here, then there is a horizontal asymptote of y equals k. where k is the ratio of their leading coefficients. Sounds kind of weird, but I'll work it out with this example. For example, x cubed plus 3x minus 1 over 1 minus 2x cubed plus 4x has a horizontal asymptote of y equals -1/2. Right, so they have the same degree. Right, the biggest power is 3. When you have the same degree, you have to look at the ratio of their leading coefficients. And I'll remind you that is the number multiplying the biggest power of x. So the top leading coefficient is 1. The bottom leading coefficient is -2. And the ratio just means you divide them exactly like they're written. 1 over -2. So more simply, we write -1/2. And that's a horizontal line, so it's y equals -1/2. Right, now, especially with fractions, sometimes it's not as easy to see exactly that it's a fraction on the graph, but we'll go ahead and graph this. To make it not too messy, I don't think actually, let's go ahead and put it all on the same one for the time being. So the numerator is x cubed plus 3x minus 1. And the denominator is 1 minus 2x cubed plus 4x. Minus 2x cubed plus 4x. I'm going to go to the standard window. All right, so one thing I'll point out here, this last example we did, it's very messy in between. But once again, we're only caring about what happens to the right and to the left. If you look at what it's going to towards the right and left, it looks like the same y value. Now it does look like it's sort of going to 0. So how can you tell that it's actually going to -1/2 and not 0? Well, if you think about what we're saying when it goes to the right or to the left, we're talking about plugging in really big x values. If I'm going towards x equals infinity, I could plug in like 1,000,000 and see what it is. So if I go to my table, let me clear all this stuff out. Oh, can I not do it like that? All right, well, I'll do it this way. If I plug in like 1,000,000, let's say. All right, this was the first graph. That didn't have a horizontal asymptote. This was the second graph, which was 0. And this is really confirmed here. What this means is we have about 10, but we move this decimal over 13 spots. So it's a 1 with 12 zeros in front of it for the decimal. And if we go over to our last one, you can see this is basically -1/2, -0.5. So it does confirm our horizontal asymptote. Usually, if you plug in a big enough number like that, that's plenty. You don't need to do more. If you want to plug in an even bigger number, you can do that. And you'll see, based at this point, it's so close to -1/2 that the calculator can't even round it away from -1/2 like it could up here. It doesn't have enough decimal spots in it. So that's how we can look at horizontal asymptotes on graphs. Definitely, when you have one and you have to look at this ratio, you really got to know what you're looking for to get it right. It's definitely best just to do it algebraically, but you can use your calculator to confirm it. All right, so I have one question here before we get to the graphs. It's putting it all together. Basically, if you have a rational function, what things could you possibly be interested in figuring out? Well, we have pretty much all the new stuff here, the domain, vertical asymptotes and holes, all that goes together as we saw. We have our other new thing, which is horizontal asymptotes. We may or may not have one, as we discussed. And then we have some old ideas. We have x-intercepts and the y-intercept. All right, so I'm going to do the domain part first. I'm just going to go kind of in order, but with the domain, I'm going to do the vertical asymptote and hole as well. But remember, for the domain, we set the denominator equal to 0 and solve that. And once again, you'll probably be able to factor everything in this section. If you aren't comfortable with factoring it, you use the quadratic formula. But factoring without a 1 there, that's something you need to learn how to do. And I'll just briefly go over that again. If you use the AC method, you don't use gets and check. You multiply the 2 and the negative 12 is negative 24. And we want two numbers that multiply to add. Two numbers that multiply negative 24 and add to negative 5, and that would be negative 8 and 3. Right, now the way to get negative 8, when you FOIL out, the 2 can go with negative 4, and the 1 can go with a positive 3. And those will check out. If we FOIL this out, the last parts will give us the negative 12. Right, so we've got it factored. We set each part equal to 0 and solve it. Right, the one on the left here, we get negative 3/2. And the one on the right, we get 4. Right, things we've been talking about all chapter. Right, we want to write the domain. It doesn't say in the directions, but it's always interval notation. Let's go ahead and do that. We got negative infinity. Remember, we start all the way at the left, go to our first number in order, negative 3/2. Stop there, jump across it, go to our second number if we have one, which is 4, and then jump across that. We would stop at a third number if we had a third number. We have no more restrictions after 4. We go to infinity. Okay, so that is our domain. Right, and then the thing that goes along with that, the vertical asymptotes and the holes. We need to factor and cancel everything. And especially if you do enough of these, you realize once you factor it, you can directly see what may or may not cancel, and you don't actually need to physically cancel them. So we already factored the denominator, which was 2x plus 3 and x minus 4. And then the top, you can also factor this. 2 times negative 1 is negative 2. Two numbers that multiply to negative 2 and add to 1 would be 2 and negative 1. But the numbers here are so limited. If you're used to the guess and check method with these factoring, you only have two options really, because numbers that multiply to 1 can only be 1 and 1. And you just ask the question, which one does the plus go on, which one does the minus go on, and the plus would go on this one. All right, so if you FOILed this out, the inside part would give you 2x minus x, which is 1x. But the thing to notice here, we factored it. There are no factors in common. So nothing cancels, which means, there are no holes. Holes come from what cancels. And both of the x values, negative 3/2 and 4, are vertical asymptotes, We have vertical asymptote of x equals -3/2 and x equals 4. As we talked about before in the previous part. Okay. All right, so we did everything that I've underlined in purple here. We got the domain. We figured out there are 2 vertical asymptotes and there are no holes. All right, I'm just going to go in order now. The y-intercept. For the y-intercept, you always plug in x equals 0. Whenever you do an intercept, you plug in the 0 for the opposite thing. And what you'll notice here, if you plug in 0, is the way it's written. You really want to use this and not the factored version. It's just a little easier, I think. But it doesn't really matter. I just like to use the easier version. Normally, I wouldn't actually write all this out plugging in the 0 when I do it on my own. Because what happens when we plug in 0 is all this stuff with x's becomes 0, and we'll be left with the -1 on top and the -12 on the bottom. Right? This is 0, this is 0, this is -1 on the top, this is 0, this is 0. We got -12 on the bottom, and -1 over -12. The negatives cancel to give us positive 1 over 12. But do remember the y-intercepts are coordinate pairs. We have x is 0 and y is the 1/12. And I think one thing that's worth mentioning, it is possible that 0 is not in your domain. If 0 is not in your domain, you can't actually plug it in, and you wouldn't have a y-intercept. So don't try to force yourself to have a y-intercept if you can't. X-intercepts. We could have 1, we could have 2, we could have 1,000,000, we could also have 0, just depends. But what do we do when we do figure out an intercept? Is we plug in 0 for the opposite thing. All right, we plug in 0 for y or f of x. This is one where you definitely want to use the factored version. So we got 0 equals, the factored version over here is what I'm going to use. 2x minus 1 times x plus 1 over 2x plus 3 times x minus 4. Right. Now, one thing that can really become a shortcut when you're finding the x-intercepts of a rational function, because you have a 0 over here, if you get rid of the denominator by multiplying each side by the 2x plus 3 times x minus 4. Right, it's sort of almost like half cross multiplication. If we had a 1 over here, we would cross multiply. Right, the denominator on the right side cancels with the numerator because we multiplied it on purpose, but the right side, or left side rather, we're multiplying by 0. It doesn't matter what this stuff is. The left side is just 0. So 0 equals 2x minus 1 times x plus 1. And now, if you set each one equal to 0 and solve, we would add the 1 and divide by 2. The first one would be 1/2, and the second one we'd subtract the 1 and get -1. Okay. Those are the x values of the x-intercepts, or the zeros as we were calling them before. If you want to write the x-intercepts, they need to be coordinate pairs. The x value is this, and the y value is 0. Well, let's do that right through there. So x-intercepts, you can really see a lot when you figure out the domain. You actually do a lot of the setup for everything. Because really outside of that, all we've done really is plug in 0 to get the y-intercept. Right, the last thing we want to figure out is the horizontal asymptote, and this is very quick. You just got to remember the rules. And this one, remember you're looking for a horizontal asymptotes at the degrees. The degrees are the same. If the degrees are the same, we take the ratio of their leading coefficients. We have y equals 2 over 2, which equals 1. But be careful here, it is an equation like the vertical asymptotes. Y equals 1 is our answer. So let's go. I'm just going to go ahead and box in the answers. I didn't do that as we went. Those were the x-intercepts. This is the horizontal asymptote. This was the y-intercept. This was the domain. We had no holes, and we had 2 vertical asymptotes. If that is, when you're given an equation of a rational function, that's pretty much anything you could be interested in. Right, so the last thing is the graphs of rational functions. If you were comfortable with the graphs of polynomial functions making their equations from a description or from the graph, all this really brings into it is the vertical asymptote aspect. And you can bring the horizontal asymptote aspect a little bit into it. That comes from the last part. But I'll remind you, if there's an x-intercept, then what that means is x minus c is a factor. Now that we're talking about rational function, it's going to be a factor of the numerator. X-intercepts are factors of the numerator. We can see that working up here. If there is a vertical asymptote at x equals c, then x minus c must be a factor of the denominator. Okay, so remember, our vertical asymptotes come from the denominator equaling 0. Okay, you don't have to worry about holes in this section because we cannot see holes on graphs. One thing that talk about here, the multiplicity. Remember the multiplicity for a x-intercept, it's 1 if it passes through, and it's 2 if it only touches the x-axis. For vertical asymptotes, the multiplicity is 2 if the vertical asymptote comes from the same side. And I'll actually explain this with a picture. We'll see it in a graph. But on the graphs, if you have a vertical asymptote, you're going to see a dashed line. That is a terrible vertical asymptote. So I'm going to have 2 of them here just to explain. That's at x equals 1, and this is at x equals -2, vertical asymptote. If it's coming from the same side, meaning maybe at -2 it's going towards the bottom both ways, same side. And I guess when I say that, I mean same side of the x-axis. It's going below, it's going towards -infinity. It's going the same way. They're both going down. They could also both go up. The multiplicity equals 2. Or in general, it would be any even number, but we use 2. If it goes towards the different sides, let's say at x equals 1, from the left it's going down, but on the right it's going up. So different sides, one's going to the bottom, one's going to the top. Then the multiplicity equals 1. And I'll just remind you that's similar to the x-intercept thing. If it stays on the same side, if it only bounced off the x-axis, the multiplicity we used is 2, and if it passed through, the multiplicity was 1. Right, so that's really the main added step. The last thing that we did when we figured out all those after the multiplicities and the x-intercepts, we figured out the leading coefficient. In the problems, we were either told the point it goes through, in the graphs, we figured out the y-intercept and used that. Now you actually could use the horizontal asymptote, which we'll see as well. All right, so the first couple I have here are descriptions, and then the last one will be a graph. This first one, what you'll notice for these written ones is there's no mention of multiplicities. We're just going to assume all multiplicities are 1. All right, if you aren't told, just assume the multiplicity equals 1. With the graphs, we have to figure out the multiplicity of what's going on here. But this isn't going to be as bad as it sounds like. Vertical asymptotes, you'll be told some of those, x equals 5 and x equals -8. What that means is we have x minus 5 and x plus 8 are factors. And they're factors of the denominator because they are vertical asymptotes. All right, so remember, if a vertical asymptote is at x equals c, then x minus c must be a factor of the denominator. All right, we're assuming the multiplicity is 1. We could write that 1 in here if you want, but those are factors of the denominator. We are told that we have x-intercepts at -6, 0, and 4, 0. Well, x-intercepts are telling us what our factors of the numerator are. We got x plus 6 and x minus 4 are factors of the denominator. Sorry, not the denominator, the numerator. I used the denominator so much, and that was a slip up. Right, so these things are going to tell you all the important factors. The y-intercept is going to tell you how to figure out your leading coefficient A. It's not telling you it's 2. It's telling you what to plug in to figure it out. Right, so the way this really works, when you make a rational function, you have A in front, your leading coefficient. Then I make my fraction. I have my factors of the denominator, which I'm going to go ahead and put in, x minus 8 and x plus 5. We figured that out before. And then the factors of the numerator are x plus 6 and x minus 4. Once you have all this figured out, plugged in, and it'll come pretty quickly, we want to figure out A, and we want to plug in x equals 0 and y equals 2. So we plug in x equals 0 and y equals 2 to get A. Let's go ahead and do that. The f of x is y. We got 2. Solving for A. Multiply. We have 0 for x everywhere. And 0 plus 6 and 0 minus 4 on the top. On the bottom, we've got 0 minus 5 and 0 plus 8 on the bottom. You know, once again, just simplify as much as you're comfortable with at a time. On the top here, we got 6 times -4 is -24. over -5 times 8 is 40. -40. The negatives cancel. I'm going to go ahead and mark that off. And we can simplify 24 over 40. We can take a 4 out of each. We can take an 8 out of each and get 3 over 5. Now to finish getting a, we would just multiply by the reciprocal, multiply each side by 5/3. And we get a equals 5 times 2 is 10 over 3. So what I'm going to go ahead and do is just plug that in there. And we get our final answer. F of x equals 10 over 3. You can leave it like this. Times x plus 6 times x minus 4 over x minus 5 times x plus 8. And that is our answer. Right, so once again, vertical asymptotes, they give you factors of the denominator. X-intercepts give you factors of the numerator, and you'll either be given the y-intercept, some point it passes through, or as you see from the next one, horizontal asymptote to figure out a. All right, I'm going to leave this in view while we do the next one. All right, similar setup. We want to figure out the equation of a rational function, vertical asymptotes of x equals 6 and x equals 4. So this is telling us we got x minus 6 and x minus 4 are factors of the denominator. And then we have x-intercepts of 3 and 0, 3, 0, and 5, 0. So we got x minus 3 and x minus 5 as factors of the numerator. And we got our a out front. We'll use this to solve for a. At first, this is going to seem really challenging, but we'll see the way it works out. It's pretty nice. Okay, so we got f of x equals a out front. Our numerator, we got x minus 3 times x minus 5. And we've got our denominator, x minus 6 times x minus 4. Now the question right away is, how are we going to use this to get a? How do we figure out the horizontal asymptote of this thing? Well, what you want to notice here is that a is just a number. If you look at the degrees here, if we multiply these out, these both have degree 2. And remember what we talked about, if the degrees are the same, that means their horizontal asymptote is y equals the ratio of their leading coefficients. All right, now I'm going to multiply these out so I can explain this a little bit better. You don't need to actually do this in the problem. But if you FOIL out the top, you get x squared minus 8x plus 15. And on the bottom, you get x squared minus 10x plus 24. What you'll notice is their leading coefficients are 1. So that would tell us we have a horizontal asymptote of y equals 1. To make it 7, we simply just put a 7 here for A. Right. So what happens if we plug it in, just so you can see the final answer, and we can graph it so it makes sense as well. What we're doing here is kind of a reverse of what we normally do, since the horizontal asymptote of this thing would be A, because if you think about distributing this, the leading coefficient on the top would be A, the bottom would be 1, that's supposed to be 7. So we got f of x equals 7 times x minus 3 times x minus 5 over x minus 6 times x minus 4. And I'm just going to go ahead and graph this real quickly to show you that the horizontal asymptote thing works. Get rid of all these. We got 7 times, and then we have multiple things on the top, so I gotta put a double parentheses, x minus 3 times x minus 5. That's our numerator. We divide by our denominator, which was x minus 6 times x minus 4. Okay. Now this one, you can't really see what's happening to the right. We can zoom out. But remember what I showed you before is you can just plug in a really big number. So if we go to second table, and if you plug in a really big number that's already down here, a million, you know, we got 7 basically. If we plug in a billion, it was still 7. So the horizontal asymptote is 7. If you mess around with this number up front here, this is just gonna change your horizontal asymptote to this number. So if I wanted the horizontal asymptote to be -9, I would put -9 here. I could graph it, but if I just go to my table, you'll see that affected right there. So the way these problems work, if you are told the horizontal asymptote, it's gonna be actually telling you the A value. A equals 7. All right, so the last thing in this section is writing an equation for a rational function given its graph. For these, what you do is you kind of write down your information like it's given here and then use it. So sometimes you'll see the y-intercept and you'll use that to figure out A. Sometimes you will see a dashed horizontal line for the horizontal asymptote, and that's telling you A. I'm just doing one of the former. All right, but let's write down the x-intercepts along with their multiplicities. The only x-intercept we have here is 2. Don't worry if you can't see something on the picture, it's not there. This isn't going to hit 0. Not going to have another x-intercept. We got an x-intercept at 2, 0. Since it passes through, its multiplicity is 1. That is the only x-intercept. And remember, the x-intercepts give us factors in the numerator. So we have a factor of x minus 2 to the first power in the numerator. I'm going to do x-intercepts and vertical asymptotes first because that's what forms our factors. Here we have 2 vertical asymptotes. They will be given as dashed lines because you can't actually know from the graph if it's perfectly there. So we got x equals -1 and x equals 4 are our vertical asymptotes. At x equals -1, they're going opposite ways. One's going down and one's going up as we go to the left and to the right. So its multiplicity is 1. And then the other vertical asymptote we have is that x equals 4. What you'll notice here is that these are both going down, going the same way. Right? So from the left it's going down, from the right side it's going down. So its multiplicity is equal to 2. Right, so I'll write a reminder here of why that is, but it's coming from what we talked about up here. All right, so this is telling us our factors of the denominator. We have x plus 1, our opposite sign to the first power, and x minus 4 to the second power. All right, the last piece of information that we're going to need to use to figure out a, like we did before, is the y-intercept. And the y-intercept is at 0, 2. Right, but once again, I'll remind you with the y-intercept, this isn't necessarily the a value. You have to plug it in to figure out a. Right, so f of x equals a times the factor of the numerator. We only have x minus 2. Over the factors of the denominator, we have x plus 1 and x minus 4 to the second power. All right, now let's go ahead and plug in x is 0 and y equals 2 to get a. We've got 2 equals a times 0 minus 2 over 0 plus 1 times 0 minus 4 squared. Just simplify as much as you are comfortable with at a time. We got 2 equals a times the numerator here is negative 2. The denominator here, we have negative 4 squared is 16 times 1, which is 16. You can simplify this fraction or just directly multiply by its reciprocal. It does, and simplify later. It doesn't matter. I'm going to do the reciprocal now. So we got 16 over negative 2 is what we're multiplying each side by. To get this to cancel out, get a by itself. And we get a equals, actually pretty convenient, on the left side the 2's cancel, the negative sign's still there, negative 16. And we go ahead, once we figure out our a, like all the others, we plug it in and write that as our final answer. Okay, so I'll write it over here. I've got plenty of room. F of x equals negative 16 times x minus 2 over x plus 1 times x minus 4 squared. All right, and if you want to, you can graph this. Now this is the last question, but I'm going to go ahead and graph this, and you can see that we'll have the same y-intercept, we'll have the same vertical asymptotes, it'll look exactly the same. So we got negative 16 times, oops, it's not a time symbol. On top we had x minus 2 divided by the bottom. We had on the bottom x plus 1 times x minus 4 squared. Go ahead and hit graph. Our vertical asymptote is at negative 1 and 4. Right, just to compare, that works out. the shape looks exactly the same to the left of the vertical asymptote, to the middle, and to the right. They all look the same. We have a y-intercept at 2, x-intercept at 2, and the vertical asymptotes look correct around it. It's going down and up this one on this one, and it's going down and down on this one. But one thing now I like to point out is that this -16, this has nothing to do with the horizontal asymptote here, because the degree of the denominator here is much bigger. It's 3 than the numerator. So this has a horizontal asymptote of y equals 0. This number doesn't affect it. But this is chapter 3. This is the end of chapter 3.